But when you wish, you can start.
All right, then I'll just start. So I already did this first exercise in my exercise group yesterday, but Florian didn't get to that, so I'll repeat it here again. So we're now talking about the scale dependence again, and the aim of this exercise is to show this formula here using what Marcus had derived in the lecture. And we will now also see why this delta here he introduced comes in handy. And so what I also wrote here already is that using this, so we will use this equation here iteratively. And from this, we see that alpha s scales as 1 over L for large L. And this is what we will use now. And so if we invert this, we will get the following. That our, oops, let me know. Yeah. What can I write? Okay, so I'm having issues again. What's going on now? Okay, now it's working. We invert this equation, then we find that alpha s equals just the thing above, so B naught L plus B1 log 1 over alpha s. So where I'll leave out the, I can just write it. The mu minus B naught delta plus something that's of order L to the minus 1. And so we have to take the inverse of all of this. And so here I already, what Marcus had written this as a log of alpha in the lecture, but I already switched the sign here. And because now we will plug in there again the expression that we had for 1 over alpha s. So we do this iteratively. Let's do this in a side note here, because we can use that the log of 1 over alpha s is the log of B naught L plus something that's of the order of log of L. Right, and this we can expand in L. And if we do this, we find that this is the log of B naught L plus something that's of the order of L to the minus 1. And how we do this is we can separate off, so we can basically pull the logs apart and write it as log B naught L plus log 1 plus something that's order of 1 over L, and then we can expand this log around its argument of 1 and find that this is just this here. And so if we plug this in here, then we get here a plus B1 log of B naught L minus B naught delta, and again these terms, these higher order terms, which we don't really care about right now. So let's operate now. Bottom of the page. All right, and so here we can now expand this in L for large L. And if we do this, we then find that this is just following expression here, which is already pretty close to what we wanted. First two terms already look exactly like what we had to show. And now we've got another term. It's like V naught L, V naught delta minus V1. Oh, oops, sorry. The log apart here. So here we want just the log of L, because then we have the log of V naught here. Plus terms that are order L2 minus 3. And so here, this expression here, for a clever choice of delta, this is 0 for delta equals V1 over V naught times the log of V naught. All right, so this is what we had to show. And this already also explains why it's really useful to use this delta parameter here. So this one here. Are there any questions regarding this exercise? No? Okay, then I'll move on to the next one, where we had to show that the scale dependence of an observable really has only residual scale, so that this observable has a residual scale dependence that's of order alpha as n plus 2. Yeah. Of order alpha squared. So what we had to show, let me just start here. Great. And then what we had to show, that the scale dependence, so P squared of C of mu is of have a look at the exact form what we're supposed to show, or how it was written in. That's wrong. Sorry, I need to pull up the correct slides. By the way, am I only sharing the notebook, or can you also see the slides that, of the lecture which I'm having on screen?
We have simply seen a whiteboard on which you are.
Okay. So I'm only sharing that window, so I can't actually share the exercise. Maybe I should have done that differently. Yeah. Okay. No. Then I probably might want to unshare that. Just a second. Sorry. Okay, I assume you all have the exercise set on your device, right? Okay. Yeah, just this here was a Q, right? No. So this is of order alpha s squared. So where I will now, that's why I was having a look, because we first need the definition. That's following. These first coefficient functions C naught plus a higher order term So we should now show that the scale dependence of this is of order alpha s squared. And so we just plug in the results we have from the lecture. So for this, we use in particular, we need the scale dependence of alpha s, which is just given in terms of the beta function. Do this, we then find that this is, and then use simply the chain rule and get the following results. So this is minus n naught plus these higher order terms here. Square. And then we have an additional term that goes like then here we readily see that this term here cancels against that one here. So we're only left with the higher order terms. So these are indeed as we set out to show. So let's briefly walk through these terms here and how they arise. So if we take the leading order term, if we just take the derivative, we just have the derivative of alpha s, and that gives us this first term here. So we got one less power from taking the derivative, And then we've got 2 additional powers from the first order term of the beta function. And I also neglect all the higher order terms of the beta function. And so here in this second part, we then have here a alpha s to the n plus first power. And doing so here, the derivative with respect to this alpha, we also get here one more power. And then if we, however, go to the exactly. And this also multiplies the second term. So this here. Okay, right now. Oops, sorry, there's just thought so. There's something missing here. Okay. Why can't I write? Sometimes the behavior of the software is kind of erratic. And also, and then the third term comes from just taking the derivative of this explicit log mu term here. And so this is what we are left with, and the lowest order terms constant, we're left with the higher order terms, and so n plus 2 obviously missing here. Okay, so this is that. And then I'm going to start a new page. Should be good. And then we have another exercise where you were supposed to calculate solve the scale dependence of m, so the quark mass, because it also has a running as a result of renormalization. And so the equation for this that was derived in the lecture so we can derive the quark mass at given the quark mass at a certain scale, we can get it at any other scale. If we just evaluate this expression here. So where we have the anomalous mass dimension, and again, the QCD beta function. So, and here we are supposed to evaluate this with the anomalous dimension and the beta function at next to leading order, where they're given by beta function. We've seen by now many times. For this, we get the following expansion in alpha S. Structure is exactly the same as the anomalous dimension, but we've got one more power up front. Yes, and then we expand this ratio of the gamma function of this anomalous mass dimension and the beta function in alpha S, because so we want this ratio at next to leading order. And doing this, we then find that gamma m of alpha s over beta of alpha s is just C naught over B naught times 1 plus C naught over B naught times C1 minus B1 plus higher order terms. All right, and then with this, we can actually really easily solve the integral in the above equation, which you can't see right now, unfortunately. And we can then write our integral from the lower boundary to the upper boundary, so from the initial scale to the final scale. So this is C naught and B naught times the log of alpha s at the final scale over alpha s at the initial scale. That's the leading order term plus C naught over, oops, just see that there's a mistake here, sorry about that. And this now has to be evaluated at the scales at the two, at the strong coupling at the two scales at the lower and also the initial and final scale. So and this is then plus something that's of higher orders to neglect here now. So because this would be alpha s at the one scale minus alpha s squared at the one scale minus alpha s at the higher order scale. So okay, and so here we can already use that. Well, I'm not really using it, but we note that this here is actually of order alpha s squared, because so the strong coupling at one scale differs from the strong coupling at another scale by terms of order alpha s squared. And so this here it would then be using the same argument order. So if there are any questions, just interrupt me, please. So if we then use this, we can plug this into the expression that we had in the beginning. And get that the running mass of the core can be written as mass of the initial scale times the exponential of should stay on. So what I'm doing here now is I'm already splitting the exponential into two parts. And you will see in a moment why this comes in handy. Plus, so as I said, we neglected these higher order terms here. All right. And then we can rewrite this yet differently. The first thing here can be written as ratio of couplings at different scales raised to the power of naught b naught. Exponential, other one we can just expand with exponential series. For this,
Excuse me, we cannot hear so well, so maybe it's a problem with your microphone.
Okay, has it been like that all the time, or?
No, just in these last few seconds.
Okay, that's weird because I haven't changed anything. Is it better now?
Yes, it's better.
Okay. I don't know. Oh, maybe I had my notes over the microphone of the laptop because I'm using the microphone of the laptop. So just interrupt me if it's getting worse again. So yeah, this part here. Times alpha s minus alpha s naught. And so here we now already truncate the series, so there's no real use in expanding this any further because we already neglected the alpha s to the third power terms here. So if we went took the second term in this thing here, then we would already have alpha s to the fourth power, so which is beyond the accuracy we are having here. All right, so this is the running of the quark mass at next to leading order. And
excuse me.
Yeah.
How did you get the 1 plus C0 over B0? Where does that 1 comes from?
That's just the series representation of the exponential function.
Oh, sorry, I didn't see there wasn't the exponential anymore.
Oh, yeah,
sorry. Sorry.
No. Yeah, so that's just the series expansion of the exponential function. Yeah, and so if we now can still go back a little bit, that's the next to leading order expression, but we can also, for now, can simplify this in the leading order case a bit more, because there we just have the first term. B naught, and this can be rewritten using leading order running of the of alpha s. This can be rewritten as
So we cannot hear you. I don't know
now I didn't say anything.
Okay.
Because I'm still writing. So what I'm doing now is that I express the the coupling at the scale mu using the leading order running of the coupling in terms of the coupling at the scale mu naught. And so this just gives me this expression here. So there's a square missing here. And if I then use, so this obviously cancels out 1 power of alpha s at the initial scale. And if I then use that so the next step then only works for the following condition, that alpha s of mu naught times this log we have there is small, because then we can expand this this exponential here, and this gives us then the following result. Minus naught alpha s mu naught times the log. All right, so that's the exercise about the scale dependence. I would now, if there are any questions, bring them up now, because now I'm going on to the first part of the exercises of the second lecture, with the light cone coordinates. So are there still any questions about the scale dependence? No? Okay. Yeah, then I'll continue with the light cone coordinates. That was exercise 1 of the new sheet. So this had 3 or 4 rather small no, problems. And the first was to show some property of the integration measure. So for this, I'll first write down again the definitions of light cone coordinates. So for a given 4 vector, which we call v, which we can write in the following way. So we've got the time component and then the 3 spatial ones. We can define the following. So we've got the plus and minus components defined as v naught plus minus v3 divided by the square root of 2. And then the vector components, which are just the v1, v2 parts of the initial vector. And now we are supposed to show the, we can also, which will come in handy later, that we have the following. So in terms of the initial ones, in terms of the light cone coordinates, can be given as plus minus for the time-like part. And 3 component, that's plus minus minus divided by square root of 2. So now we have the first thing to show is that d for v equals dv plus dv minus d2 v. And so for this, we first use that we can actually, so this is what we want to show. And we first use that this is that in the initial coordinates, we can write it in the following way. So this can always be done, and then we just make a change of our integration variables, for which we need the so using these properties up here, we introduce the plus minus components, but that means that we then still need a Jacobian for that. But this Jacobian is really simple because it's just the 2x2 matrix we have to consider, and it's following entries. So if there's anything unclear, just interrupt me, please. But I hope here things should be rather straightforward. And that's obviously a minus here. So this, okay. No idea what happened now. So if I then, oh, that's not very nice. Sorry about that. And so this Jacobian is just 1 as it should be. And this finishes what we wanted to show. So the next thing we had to show was the how these derivatives are defined, and it's in particular that the plus component of the derivative is actually the derivative with respect to the minus component of the vector. So the next thing we wanted to show, or had to show, was the following. So start something new here. Definitely nicer. So we have these definitions of these dv plus equals 0 plus d3 over square root of 2, and dv minus defined in close analogy as the difference between d0 and d3. And so what we wanted to show is that this is actually d over d minus, and this here is d over d plus. And so to this end, what we do, I can scroll down now. So to this end, what we do is we actually act with this derivative on the vector, which it's so with respect to taking the derivative, and then we know what this should be. So this should just give us a delta mu, so just 4 in 4 dimensions. And so this is then just d naught minus d1. Yeah. So I'm running out of time already. When am I supposed to stop?
In 15 minutes.
Okay, so I still got some time, right? I just thought it was 45. But
as you wish.
No,
if you need time to finish the exercise, it's better if you finish the exercise.
15 minutes is fine. 15 minutes is fine.
Of course, you have to start a new exercise which takes 30 minutes.
No.
Better.
I'm just finishing these brief ones here. So now use the relations I had above for V0 and V3 to express them in light cone coordinates. This is then just so this is now exactly what we had in our definition. And so this is the d minus. And this is d plus. And since we want this here to be we can conclude that this here is actually X. So this has to give 1 as well as this one has to give 1. And from this, we can then conclude that this must be like stated in the exercise. All right, so the next exercise was then, so the next part of this exercise, which also should go rather quickly, was to consider the behavior of the light cone coordinates under Lorentz boosts. And so for this, we use that under a general boost, we have that's a boost along the z-axis. We have that a vector v goes to effectively prime, which is L times V, but this is our boost matrix, and L is a 4x4 matrix with the following entries: gamma, naught, naught, minus beta gamma. So it doesn't do anything to the 1, 2 components, as you can see, because we're boosting along the 3 component. So, and then we find that this boost mixes the 0 and 3 components of this vector. So we find that V prime equals gamma times V naught minus beta 3. And there, got nothing, as I said, on the transverse components, and here we've got gamma V3 minus beta V naught. And we can then re-express, we can then from those compute the plus and minus components of this primed vector. And that's then just gamma 1 minus beta V naught plus V3 over the square root of 2. This is then just gamma 1 minus beta V plus. And for the minus component, we find the following, that we've got now gamma 1 plus beta times V naught minus V3, and this is again divided by square root of 2, and this is then gamma 1 plus beta V minus. And so the parameter describing the boost is then this alpha, which was mentioned in the exercise, is then just this up front here, alpha V plus. And if one then uses the definition of the gamma, could have written this somewhere here, in case not everybody's familiar with it, but I think you're all familiar with this. This is 1 over the square root of 1 minus beta squared. Exactly, so beta is the velocity of the boost over in terms of c, and this is then just, so if we just use these properties, you see that actually those two prefactors are each other's inverse, and we get what we had set out to show, the simple behavior of these coordinates under boosts, which concludes my exercise for today, I'd say. Are there any questions regarding the exercises or the lecture, or? So everything's clear?
Feel free to ask questions, even if the exercises were explained in a very detailed way, so maybe everything is clear, but if you have doubt, it's time to ask.
Yeah, I'm happy if everything's clear.
The last exercise,
Yeah.
it would be possible also to write the boost in the components in terms of not the Minkowskian spacetime, but in terms of Lightfront coordinates. I mean the
Yeah, you can also write the matrix, this L here, basically.
It should be different, and so it is also possible to solve the last exercise only by rewriting the L in the new.
Yeah, absolutely.
Basis. Yeah.
So you can also make this kind of basis transform for diffuse matrix if you wish. Yeah, absolutely. Then you just get these linear combinations already in the correct matrix entries.
Yeah, I think so.
Yeah. Okay, thanks for the comment. Oh, there's something in the chat. Oh, everything's clear. Okay, good. Then let's conclude this exercise session. Tomorrow, Florian will give the exercises again. Okay.
Okay, very good. Thanks, Peter. And so we meet again in the afternoon for the lectures, and let's thank again Peter for these year's exercises.
Okay.